So this is going to be the first of 7 videos for the very first topic in IB Physics, which is A.1 Kinematics. And today's video is going to be about kinematic variables. And just before we get into that, I think it's worth quickly going through what the word kinematic actually means. You're going to be hearing this a lot in this topic. It's called kinematics. So the word kinematic is used whenever we're talking about any sort of motion that does not involve forces, or at least we don't consider the forces in the motion, right? So, okay, for example, if we have a person here, let's call him Mika. He can run to the right, he can run to the left, fall down, jump up, he can move around, right? And if we were looking at the kinematics of Mika, or his kinematic motion, we would be talking about things other than force. So just to make that clear, force is a big no-no in kinematics, right? We're not looking at force. What we are looking at are other quantities. What are the quantities? That would be things like distance, displacement, speed, velocity, and acceleration. Now those 5 variables that I just mentioned are collectively known as the kinematic variables. Yeah, so that's just what we're going to be going through today. Lots of these quantities might be pretty familiar to you, I hope, and you might feel like it's pretty basic, but hopefully this video will give you a super clear foundational understanding of what these variables are, how they behave, etc., where they're used. Yeah, and the better you are at the foundations, the easier the more complicated stuff will get. So I've just labeled these 1 and 2. These are the first and second out of 5 of your kinematic variables. Okay, let's look at them both. I've grouped distance and displacement together because they're sort of similar. They have a small difference though that you need to be super careful of. To start, distance. Distance is what we call a scalar quantity, right? Meanwhile, this is a vector quantity. Okay, just wanted to put that out there, and I'll go through them. Distance is how far something is. Pretty simple. I think we all know what that is. Say now I have a winding track. Let's bring back our person from before, Mika. There we go. He runs down this track, right? The distance he travels is the distance of the track, how long this winding track is, right? It's going in this winding circle. Say that's 500 meters. The distance he runs is 500 meters. And when we write 500 meters, we don't care about the direction he's going in, right? That's why we just write the number and the unit. We're not focused on which direction he's traveling in. That's why it's a scalar quantity. No direction is involved. I think we know this already, but if you don't, a scalar quantity is just when direction is ignored. We don't talk about direction, but we do look at the magnitude, right? The magnitude is just the number itself. So in this case, obviously, it's just 500 over here. It's actual quantity, right? Displacement, however, it's a vector. A vector quantity will look at both direction and magnitude. So how does this differ to the distance when we use it practically? Let's draw a track from before, right? A and B. Winding track. Distance along the track is 500 meters, but Mika, the guy who's running down the track, his displacement across this track is not 500 meters. Why? Because when we talk about displacement, we're looking at a starting point. Think of this like a starting line at A, and his finish point, which is B, right? Like a finish line. And we're looking at the shortest distance between these 2 points. So this line that I've drawn here, this thing right here, that is the shortest distance between A and B, between his starting and his finishing point. Okay, let's just make that clear. Start, we'll call it end point. Okay, his start and his end. And say this distance could be something like 100 meters, right? Whereas the distance of the longer track, along this, is 500 meters, right? So different quantities. Second thing to be careful of is when, now that we've got our magnitude, so this 100 here is the magnitude of displacement, make that clear, magnitude. We also have something else, as I mentioned before, over here, we have direction and magnitude, right? Both of these quantities. So now we've got magnitude, we need to find the direction. In this case, we can just make it up. Let's use our direction units. It can be north, never eat shredded wheat. Right. The direction in here is going from there to there, like that, right? It's southeast. Okay. So when we write out our full displacement, the displacement on this diagram, in this case, as it goes down this track, is 100 meters southeast. Okay. Now, in this case, I've used southeast. I just want to make it clear that the direction, it depends on your question, it depends on the scenario. You can use any form of units or way to indicate direction, but as long as it's indicated, it's fine. It's a vector quantity, it's displacement. Okay. Hopefully that's clear. I'll just give you actually one example for this. Like, for example, say I didn't want to use southeast, right? Say I was only talking about something moving right and left. I can literally just say 100 meters right, or I can just say 100 meters left. It's fine. Or in a lot of cases, what you'll actually see is they sort of label one direction as positive and one direction is negative. So for example, say to the right is positive, this way is negative. That way, say I had a ball and it went flying to the right, I'd say its displacement is plus 100 meters. And if it went to the left, I'd say its displacement is minus 100 meters. So here, instead of southeast or those cardinal directions, I'm using plus and minus to just indicate the direction. The point is, as long as it's indicated, it's fine. It doesn't matter. You're all good. It's a vector quantity. It's displacement. Okay, there you go. Hopefully that's all clear for distance and displacement, your first two quantities. One last thing. Distance has units meters, the SI units, and displacement also has units meters. Right? Why? Because they're both measured in meters. The only difference is direction, right? Direction won't affect like what they're measured in. Both are meters. Okay. Okay, yeah. Moving on now. Speed and velocity. These are now your quantities 3 and 4 out of 5. Again, I've grouped these two together because they're very similar. Same thing again with this. This is scalar. Speed is scalar. This is vector. Let's do it in a different color. Vector. Okay, vector quantity. Nice and easy way to remember this is scalar starts with S, speed starts with S, vector starts with V, velocity starts with V. Okay, so speed, scalar, velocity, vector. What are speed and velocity? Speed is specifically the rate of change of distance. So I'll actually write it out for you. It's the rate of change of distance. Now, I'm just going to quickly condense this right now. When I write change of distance, I can, in shorthand form, write change as delta, and distance usually has the symbol x or d. Either or is fine, right? Both are fine. In this case, I'm going to use d, because more direct, right? D is distance. So, yeah, let's do that. So you can write change in distance as delta d with respect to time. Okay, now time, again, we'll condense this. Time has the symbol t, small t. Okay, nice and simple. Probably already know that, just making sure. Okay, rate of change of distance with respect to t. Now velocity, again, very, very similar, but since velocity is a vector, that means that when we talk about what it's the rate of change of, it has to be the rate of change of a vector quantity. And the vector quantity that we just looked at over here was displacement. So velocity is the rate of change of displacement. I won't write out displacement in full, but displacement has the symbol S. It's a bit weird because it doesn't start with S, but it just does. Has this a symbol S, okay? And again, we can use delta here. So delta S, rate of change of S with respect to time. Exact same. So it's a very small difference again. Literally the only difference is this is this distance, this is s. Okay, but you need to know what the implications of that are to these quantities as a whole. So because speed is only made up of scalar quantities, d is scalar, t is scalar, it doesn't have direction, and direction doesn't matter, right? So say I was traveling like this at 100 meters per second. Obviously I've used meters per second here as a unit. Why? Because this statement right here can be translated directly to the formula for speed, which is just speed equals the change in distance over time. Nice and simple. Okay, quick formula. You probably already know it, so I'm not going to go focus on that too much. Okay, where was I? 100 meters per second, right? If I'm going in this direction, it doesn't matter. No need to write the direction. You're all good. You just have your magnitude and you're fine. 100 meters per second. However, for velocity, it's a little bit different. Since it's the rate of change of displacement over here, this s, we do need to write the direction. So say again, let's talk about what I was using before. Let's give us some space here. Say I have a ball. It can move to the right, it can move to the left. Let's call the left the minus direction, the negative direction, and the right the positive direction. Now, the ball's velocity in this direction is delta s over t. But this delta s, since before, if you remember the diagram before, it was plus 100. The overall velocity, which is represented by symbol v, is also going to be positive. So our velocity will be, and we're supposing time is 1 by the way, our velocity will also be 100 meters per second. Okay, positive. Just one more thing, slightly unrelated, just might be useful. You may notice that I'm using ms minus 1. The only reason for that is in the IB course, you should always be using indices to show units. So you don't want to be writing m/s. Why? Because the IB declares it as ambiguous and unclear to the examiner. I don't know why, they just do. Okay, so just use m to the s minus 1. It's the same thing because anything to a negative power is just 1 over that thing. It's just m times 1 over s, which is just m over s, right? So it is just m over s, but yeah, this is what the IB wants in terms of units. Okay, now back to where we were. So as I was saying, the velocity in the right direction is 100, positive 100. And the velocity in the negative direction, since before, if we write out our formula again, change in s over t, our t is 1. Let's just write this out in full. But our change in s, or displacement, like we said before, was minus. It was minus 100 meters. So obviously, now our velocity v that we're going to get out of it, let's not do that, let's do this, is going to be minus 100 meters to the s minus 1. Okay. Why is this important? Because what it tells us is that we're keeping the direction consistent as we move through these different measures, right? That's why velocity is always going to be displacement, s over t, not d, okay? Not d or x. X is also distance. Now that we have that established, hopefully that's clear, it's important to go over one case where they might mix up symbols. What's that case? Basically, before I said the symbol for distance was x or d, and the symbol for, let's put that in a box, symbol for displacement was s, separate, right? You'll see in some cases they're gonna mix these things up, right? The only reason they will ever do that is because when you have an object that moves a certain distance in a straight line, its displacement and its distance have the same magnitude. Obviously, you can't say they have the same direction. Why? Because distance doesn't have direction in the first place. But yeah. Okay. I'll explain this quickly. A ball rolls in this direction 10 meters, right? our distance is 10 meters, but our displacement, the shortest distance from point A to point B, is also 10 meters because it's a straight line. So that's why numerically, because the value of 10 is the same in both, when you use it in a formula, like if I was calculating the speed right now, I could do just d over t, and I can use d as displacement or distance because both are 10, right? So it doesn't matter. So that's why in some cases you will see the symbols get mixed up a bit, but mostly for the IB, this is displacement, and this is distance. Yeah, just make sure you're super clear on that. Alright, now we can move on to our next quantity. Okay, acceleration. Now, acceleration is the rate of change of velocity. Okay, we're forgetting about speed now. Okay, speed's out of the equation. We're talking about velocity. So to write that out, rate, let's do it like that. Rate of, I'll use symbols from before, delta for change, and v for velocity. V for velocity. Velocity. Rate of change of velocity with time, with respect to time. Okay. Now again, translating this word statement into a formula will give us delta v over t. Okay. Now what can we do with this? This quantity here, whatever we put into this formula, whatever it spits out at us, is the acceleration, and we represent that with symbol A. Nice and easy to remember. A is acceleration. Now, usually what you'll see is this formula is written in a slightly different way. They separate out this delta over here, delta v. They separate it out into two parts, but it's the exact same thing. You can write it alternatively as v minus u over t time is equal to a. These two formulas are the exact same thing. Okay. Just the change in velocity has just been represented by v minus u, and all that's saying is that in v minus u, let me write it out again here, v minus u, the v variable is your final velocity, and the u variable is the initial velocity. So all this allows us to do is just write it out in a cleaner way where you can input in the final and the initial velocity. So say for example, just a quick example, say there's a ball, it goes from point A to point B, what's gone wrong there, B, there we go, goes like that. It starts rolling, let's say it's already been going, it starts at 10 meters per second, and it ends up at 20 meters per second, and the time that this whole motion occurs in is, say, 5 seconds. 5 seconds. Now the reason we use that other formula is it's just less ambiguous, very clear that it's v minus u over t. Right, our initial velocity is 20, so we're going to write 20 minus the final velocity. Oops, I've done that the wrong way around there. It's the initial velocity is 10, so u equals 10. The final velocity is 20, v equals 20, and the time it takes is 5 seconds. Okay, now we just plug this all into the formula. V minus u, 20 minus 10 over 5. That's just 10 over 5. And that's 2. Now, this is the important part here. 2 meters per second squared. Okay. Now, this is actually a very common question. It does come up occasionally. It's like a one marker. Mainly, you mostly see it in ESA. It's very rare in HL, but it's worth knowing. The units for acceleration are meters per second squared. Why? Because the formula that we discussed before is A equals delta V over t. Now, if we break this all down into its actual units, we'll see that delta V, the units don't change, it's just m minus 1. Those are the units for velocity over time, and the units for time are seconds. So essentially, we're dividing distance by seconds twice. Okay? You have a second. There we go. Accidentally got rid of that. You have a second here, and you have a second here. And you're dividing distance by that twice. So that's why you're going to get meters per second twice. Meters per second squared. Also known as this. Should be writing it like this, but this is what it is, right? This times squared. So yeah, that is acceleration. Now that we've discussed all of our 5 major quantities, our kinematic variables, there's just some quick formulas or just some quick other ideas that I want to quickly explain to do with velocity and to do with speed. Now, often when you're dealing with speed and velocity, you're not going to be talking about you're going to be talking about a certain type of speed or a certain type of velocity. What are those two types? You have instantaneous, and you have the average. Okay. You'll see these quantities come into play more in future videos when we look at some of the graphs and how these variables all relate to each other. But for now, just the theory behind it, all you need to know is instantaneous is instant. You're just looking at the velocity at a certain point. So say I'm running down this track, Mika's running down this track. Say at this exact point right here, what's his velocity? Okay, that's just a theory. I won't go into how you calculate it, etc. We'll do that later. That's just a theory. The average is his velocity, again the winding track. His average velocity, very simple, it's just the average velocity across the whole thing. And you can have average speed and you can have average velocity. Again, only difference between them is direction. So for the average, I will actually tell you a formula because you do need to know it, but it's very simple, not much difference at all. When we're talking about averages, we're going to look at his total distance or displacement, divided by time, right? So it's just slight alterations to our formulas. So before our average, let's look at speed first. Average speed, it's just going to be speed equals distance, but we're going to write a small total over here. It's our total distance over time. And the time is also total. You can also write that here. Total. Okay, nice and simple, very easy. So say for example this long winding track we had here, this whole thing, say it's 500 meters, 500 meter long track, and maybe he stopped some parts, maybe he jogged, maybe he sprinted other parts, doesn't matter. The total distance 500 meters, and say Mika took a minute to finish, right? So or say it took 50 seconds, okay? It would be 500 over 50. Total distance over total time. His average speed is 10. Okay, nice and simple. And with velocity, exact same thing again, but remember, velocity is a vector. So we're using displacement. We're not talking about distance anymore. So we're going to be using the symbol S for displacement over t equals v, velocity. And again, small tweak over here. We're just going to write a small total. Total time, total displacement. Again, nice and simple, winding track. We don't look at the track, we look at the start and the end point from A to B. How far has Mika gone from A and B? And say this distance is 50 meters. And the total time he took, again, is still 50 seconds. He still took 50 seconds to go from A to B, right? Because he was going along the winding track. The time he took doesn't change. That's why our average velocity, so our V, that looks right. V is our total distance, total displacement, 50 over total time, 50 seconds. So it's 1 meter per second. There we go. Okay, 1 meter per second. Yeah, and that's pretty much all for today's video. Yeah, in the next video, we're going to be going through some of the graphs and more complicated equations as we go along this topic. But hopefully this video has given you a super solid foundation on what kinematic variables are and a nice introduction to kinematics. Yeah, see you in the next video.